Unary relational operations. Select and project. Next. The select operation. The select operation is used to choose a subset of tuples from a relation that satisfies a selection condition. We can consider the select operation to be a filter that alternatively, we can consider the select operation to restrict the tuples in a relation to only those tuples that satisfy the condition. The select operation can also be visualized as horizontal partition of the relation into two sets of tuples. Those tuples that satisfy the condition and are selected, and those tuples that do not satisfy the condition and are filtered out. Next, the notation of select operation, where C is selection condition, which is a Boolean expression. We can have a single condition like roll equals 3 or combination of condition like x is greater than 2 and y is less than 1. Symbol sigma is used to denote the select operator. R is a relational algebra expression whose result is a relation. The, the Boolean expression specified in condition C can be written in the following from where attribute name is obviously name of an attribute of relation. Comparison operator is any of the operator greater than, less than, equals, greater than, equals, less than, equals, and constant value is taken from the domain of the relation. The example of select operation. The query above is called note nested expression. Here, as usual, we evaluate the inner expression first, which results in relation, say, manager 1. Then we calculate the outer expression on manager 1, the relation we obtain from evaluating the inner expression, which results the relation again, which is an instant of a relation we input. The project operation. If we think a relation as a table, the select operation chooses some of the rows from the table while discarding other rows. The project operation, on the other hand, selects certain columns from the table and discard the other columns. If we are interested in only certain attributes of relation, we use the project operation to project the relation over these attributes only. Therefore, the result of project operation can be visualized as a vertical partition of the relation into two relations. One has needed columns, the attributes, and contains the result of the operation, and the other contains the discarded columns. The annotation of project operation, where A is the attribute list, it is the desired set of attributes from the attributes of relation, which is in R. Symbol pi is used to denote the expression which results in a relation. An example of project operations. Here we can observe that the degree number of attributes of resulting relation is 2, whereas the degree of faculty relation is 3. So from this, we can conclude that we may get a relation with varying degree on applying project operation on a relation. Hence, the degree of resulting relation is equal to the number of attributes in the attributes list.
Relational algebra operations from set theory, the union, intersection, and minus operations. The next group of relational algebra operations are the standard mathematical operations on sets. For example, to retrieve the social security numbers of all employees who either work in Department 5 or directly supervise an employee who works in Department 5, we can use the union operation as follows. The relation result 1 has social security number of all employees who works in Department 5, whereas result 2 has the social security number of all employees who directly supervise an employee who works in Department 5. The union operation produces the tuples that are in either result 1 or result 2 or both, while eliminating any duplicates. Thus, the Social Security number value 3334455 appears only once in the results. Several set theoretic operations are used to merge the elements of two sets in various ways, including union, intersection, and set difference, also called minus or except. We can define the three operations union, intersection, and set difference on two union compatible relations R and S as follow. Union. The result of this operation denoted by R union S is a relation that includes all tuples that are either in R or in S or in both R and S. Duplicate tuples are eliminated. Intersection. The result of this operation, denoted by R intersects S, is a relation that includes all tuples that are in both R and S. Set difference or minus. The result of this operation, denoted by R minus S, is a relation that includes all tuples that are in R but not in S. Example, the figure shows the names of students who are not instructors and the names of the instructors are who are not students. The Cartesian product, cross product operations. Cartesian product operations, also known as cross product or cross join, which is denoted by X. Binary relational operations join. Several variations of join exist. The sequence of Cartesian product followed by a select is used quiet commonly to identify and select related tuples from two relations. A social operation called join combines the sequence into a single operation. The general form of a join operation on two relations are A1, A2, so on and so forth, and S, B1, B2, so on and so forth. Join condition, where R and S can be any relations that results from general relational algebra expressions. Division. The division operation is suited to queries that includes the phrase for all. The division operation is applied to two relation R parenthesis Z S is equals to X, where X is a subset of Z. Let Y is equals to X minus a Z minus X, hence Z is equals to XY. Example, Y is the set of attributes of R that are not attributes of S. For a tuple to up for a tuple T to appear in the results T of the division, the values in the T must appear in R in combination with every tuples in S.
Hi, my name is Keeyan, and today's topic is about relational algebra operations from set theory. And there is the union, intersection, and minus operations. The union, intersection, and minus operations. The next group of relational algebra operations are the standard mathematical operations on sets. For example, to retrieve the Social Security number of all employees, or SSN, who either work in Department 5 or directly supervise an employee who works in Department 5. We can use the union operation as follows. As you can see the table below, the now the relation result 1 has the SSN of all employees who work in Department 5, whereas result 2 has the SSN of all employees who directly supervise an employee who works in Department 5. Now, the union operation produces the tuples, or what we call the two sets, that are in either result 1 or result 2, maybe both, while eliminating any duplicates. Thus, the SSN value of this number appears only once in the result. Next is now these are the results of the SSN in every employees. The result 1 of employees are this, but as you can see, I highlight all the same result of every result, and they have the same tuples, but not all the numbers are repeated. Now, several set theoric operations are used to merge the elements of two sets, or tuples, in many ways, including union, intersection, and set difference, or what we call the minus, or except. These are binary operations that each is applied to two sets, or tuples. When these operations are adapted to relational databases, the two relations on which any of these three operations are applied must have the same type of tuples, which means kung mag-apply ko kanina operations kay na siya the same tuples or two sets. This condition has been called union compatibility or type compatibility. Two relations, as you can see in the table I highlight, are said to be union compatible or type compatible if they have the same degree n, and if dom ai equal to dom bi for 1 less than I less than n. This means that the two relations have the same number of attributes, and each corresponding pair of attributes has the same domain. That is why the tuples or two sets are repeated. Now, we can define the three operations: union, intersection, and set difference on two union compatible relations R and S. Now, the first one is the union. The result of this operation, denoted by R union S, is a relation that includes all tuples that are either in R or in S, or in both R and S. Now, the duplicates tuples are eliminated, which means kung naay mo usab na tuple sa R or sa S, kay automatic na siya mawala or eliminated. Now, the next one is intersection. The result of this operation, denoted by R intersection S, is a relation that includes all tuples that are in both R and S. It means na mura gyapon siya union, pero ang kalayan lang niya kay naay ang two sets or tuples kay naa sa R ug S. Now, the last one is the set difference, or what we call minus. The result of this operation, denoted by R minus S, is a relation that includes all tuples that are in R but not in S. It means na ang tanan two sets or tanan tuples na naa sa isa ka table kay wala sa pikas na table. Now, the next one is the relational algebra and relational calculus. Relational algebra and relational calculus, we will adopt the convention that the resulting relation has the same attribute or attribute name. As the first relation R, it is always possible to rename the attribute in the result using the rename operation, which means pwede nimo siya mailisan anytime basta magamit ng kag-rename operator. Remember that both union and intersection are commutative operation. That means ang union of intersection kay mura lang siya og parehas commutative, mura dali lang nimo siya makuan sa operation. And this is the R in union S is equal to S union R. And R intersection S is equal to S intersection R. Both union and intersection can be treated as n-ary operation. Applicable to any number of relations because both are also associative operation. That is, as you can see the table below, highlighted table. Now, the minus operation is not commutative. That is, in general, R minus S is not equal to S minus R. Now, next one is the relational algebra and rational calculation. Remember that intersection can be expressed in terms of union and set directions as follows. The table. Now, in SQL, there are three operations: union, intersect, and except, that correspond to the set operations described here. In addition, there are multi-set operations: union all, intersect all, and except all. That means that they all do not eliminate any duplicates, or that do not eliminate duplicates. Relation students and instructors, figure A, are union compatible in their tuples represents the name of student and names of instructors. As you can see, the student A, instructor A are the same, union compatible. Union compatible ni sila sa two sets or tuples. Now, the result of the union operation in figure B shows the name of all students and instructors. Note, the duplicate tuples appear only once in the result. That means wala na siya balik-balik o giisa na lang siya sa tanan. It means giisa na ang student o ang instructor. Wala na gibalik na pangalan o wala na gilahi na pangalan. The next one is the result of the intersection operation figure C includes only those who are both student and instructor. And the figure D shows the name of student who are not instructors, and figure E shows the names of students who are not shows the names of instructors who are not students. Sorry. Now, kita na to diri na gilahi na ang student na dili instructor o instructor na dili student. That is all. Thank you.
Hi, Alan here to report about the next topic, which is the Cartesian product, or also what we call the cross product operation. To know more about this, let's dive in. The Cartesian product, also called as the cross product operation. This is used to combine information from any two relations. In other words, we cross-join each relation which returns all the row in all the tables in a query. So how it works? Each row in the first table is paired with all the rows in the second table. In other words, it combines the tuples of one relationship with all the tuples of the other relation. Binary relational operations, join and division. Join operation is used to combine related tuples from the two relations into single, longer tuples. This operation is very important for any relational database with more than a single relation because it allows us to process relationship among relations. The goal of creating a join condition is that it helps you to combine the data from two or more DBMS tables. The tables in DBMS are associated using the primary key and the foreign key. Cartesian product versus join. So in conclusion, in join, only the combination of tuples satisfying the join condition appear in the results, whereas in the Cartesian products, all combination of tuples are included in the results. Hi, thank you so much for listening, and I hope you learned something today. This has been Alan. See you around.
Hello everyone, my name is Rexiel Alexis H. Matiao, and today we are going to talk about the different variations of join, especially the equijoin and natural join. The join operation, denoted by S, is used to combine related tuples from two relations into single, longer tuples. In relational databases such as SQL Server, Oracle, MySQL, and others, data is stored in multiple tables that are related to each other with a common key value. Accordingly, there is a constant need to extract records from two or more tables into a results table based on some condition. In SQL Server, this can be easily accomplished with the SQL join clause. Join is an SQL clause used to query and access data from multiple tables based on logical relationships between those tables. In other words, joins indicate how SQL Server should use data from one table to select the rows from another table. Before we proceed to different types of joins, first we have to know what is tuple. So tuple is a single row of table which contains a single record for that relation. This is the picture of the tuple, the purple one. So equijoin, a join where the only comparison operator used is equal or equivalence. A special case of conditional join, and as values of two attributes will be equal in result of equijoin, only one attribute will be appeared in result. Before we proceed to normal join, let us discuss the difference between equijoin and natural join. Natural join automatically join the two tables and columns which have equal name, and in the result, the common column would appear one time. But in equijoin, we explicitly mentioned the condition that on which column we have to do equality test, and also the columns would appear twice. Okay, proceed to natural join. Natural join, denoted by asterisk, was created to get rid of the second superfluous attribute in an equijoin condition. Natural join can only be performed if there is a common attribute column between the relations. The name and type or domain of the attribute must be the same. Natural join does not use any comparison operator. It does not concatenate as well, or concatenate means adds two or more strings together like the Cartesian product does. It will also return the similar attributes only once as their value will be same in resulting relation. It is a special case of equijoin in which equality condition hold in all attributes which have same name in relations R and S. The standard definition of natural join requires that the two join attributes have the same name in both relations. If they the same ang name, it requires renaming. Alright. Suppose we want to combine each project tuple with the department tuple that controls the project. Based on this table shown in the screen. The following example, first we rename the D number, the D number attribute of department to dnum, just like this, so that it has the same name as the dnum attribute in project, and then we apply natural join. So it will become proj depth to project join condition, dname, dnum, manager, SSN, start date, department. The attribute dnum is called the join attribute for the natural join operation because it is the only attribute with the same name in both relations. In general, the join condition for natural join is constructed by equating each pair of join attributes that have the same name in the two relations and combining these conditions with AND. Notice that if no combinations of tuples satisfies the join condition, the result of a join is an empty relation with zero tuples. In general, if R has NR tuples and S has NS tuples, the result of a join operation R join S will have between 0 and NR join NS tuples. The expected size of the join result divided by the maximum size NR NS leads to a ratio called join selectivity, which is a property of each condition of join condition. If there is no join condition, all combinations of tuples qualify and the join degenerates into a Cartesian product, also called cross product join. As we can see, a single join operation is used to combine data from two relations so that the related information can be presented in a single table. These operations are also known as inner joins. To distinguish them from different join variations called outer joins. Informally, an inner join is a type of match and combined operation defined formally as combination of Cartesian product and selection. Note that sometimes a join may be specified between a relation and itself, as we will illustrate section 8.4.3 for the next reporter. The natural join or equijoin operation can also be specified among multiple tables leading to an n-way join. For example, consider the following three-way join. Three-way project dnum, the number, department, manager, SSN equals an employee. This combines each project tuple with its controlling department tuple into a single tuple and then combines the tuple with an employee tuple that is the department manager. Kadagan na to tuple, eh. The net result is a consolidated relation in which each tuple contains each project department manager combined information. In SQL, join can be realized in several different ways. The first method is to specify the in the where clause along with any other selection conditions. This is very common and is illustrated by queries in section 6.3.1 and 6.3.2 as well as by many other query examples in chapter 6 and 7 by other reporters. The second way is to use the nested relation as illustrated by queries in section 7.1.2, and another way is to use the concept of joint tables as illustrated by the queries in section 7.1.6. The construct of joint tables was added to SQL2 to allow the user to specify explicitly all the various types of joins. Because the other methods were more limited, it also allows the user to clearly distinguish join conditions from the selection conditions in the where clause. Next, 8.3.3, a complete set of relational algebra operation. Algebra. Okay, these were the signs that you can see in relational algebra. This is identical or equal pero na ikatulungan line identical, sigma select, pi projection, u union, and kaning p sign kay row ang pagbasa. Rename operation and kining minus is set difference and kining row multiplication is Cartesian product. It has been shown that the set of relational algebra operations kato sigma, pi, union, row, set difference, x is a complete set ay silang ito. Any of the original relational algebra operation can be expressed as a sequence of operations from this set. So, so for example, the intersection operation can be expressed by using union and minus as follows. R intersection S is identical to R union S minus R minus S minus S minus R. Although strictly speaking, intersection is not required, as another example, a join operation can be specified as a Cartesian product followed by a select operation as we discussed. R join S is identical to select R Cartesian product S. Thank you. Similarly, a natural join can be specified as Cartesian product preceded by rename and followed by select and project operations. Hence, the various join operations are also not strictly necessary for the expressive power of the relational algebra. However, they are important to include as separate operations because they are convenient to use and are very commonly applied in a database applications. Other operations have been included in the basic relational algebra for convenience rather than necessity. Dili siya need, pampaisi lang siya sa mga bagay-bagay. We will discuss one of these, the division operation, in the next section by the next reporter. Thank you.
Additional relational operations. Some common database requests which are needed in commercial applications for RDBMS cannot be performed with the original relational algebra operations described in section 1 through 8.3. In this section, we define additional operations to express these requests. This operation enhance the expressive power of the original relational algebra. So, ang additional relational operations is mauna siya ang symbol o ang relation operation sa database. Dire sa additional relational operations, pag makakita kag ing-ani nga sign, kane, intersection, meaning defines a relation consisting of a set of all tuple that are in both A and B. Pag makakita kag ingon ani nga sign nga baliktad nga U, kay meaning intersection na siya. Nya magkapareho ang duha ka table. Diri sa additional relational operations kay nadri ang Cartesian product. Cartesian product is helpful to merge column from two relation. Meaning operation para mag-merge ang column sa duha ka set. So, nako example sa Cartesian product mo ni siya. Ayan ni siya pag-type 5 4 3 2 1. Select table 1, table 2. Table 2 tos a name sa merge from name pangalan na amot kinsa imong ibutang, tapos kaniha kani kay ano ni siya kanang naka caps lock. Naapod diri sa additional relational operations ang inner join. Inner join includes only those tuples that satisfy the matching criteria. Ang inner join is nasa lay magkapareha na column. Naapod ko example sa inner join dara. Select column underscore names ang from kay caps lock. Table 1 inner join caps lock. Table 2 on table tuldok column underscore name equals table 2 tuldok column underscore name. Muna siya ang pag-type nimo sa inner join. Tada. Diri na ta sa generalized projection. Generalized projection operation extend the projection operation by allowing functions of attributes to include in the projection list. The generalized form can be expressed as fr1, fr2 hangtod f4. So, diri sa generalized projection kay naa ang pi na sign. Pag makita kag pi na sign, mo na siya ang projection. Mo ni ang pi na sign o basin nakalimot na mo ba dara. So, projection eliminates all attributes of input relation but those mentioned in the projection list. Naapod diri sa generalized projection ang union operation. Union is symbolized by symbol. It includes all tuples are in tables A or in B. Pag union operation kay kabaliktaran sa intersection, so mo ni ang kabaliktaran sa intersection.
Hello.
I am the reporter for the chapter 8 4.4 outer join operations, and we're gonna discuss outer join operations. So outer joins are a set of operations. Outer joins were developed for the case where the user tables are to be combined by matching corresponding rows, but without losing the ones to keep all the tuples in R, all those in S, or all those in both relations in the other relation. This satisfies the need of queries in which tuples from to the result of the join, regardless of whether or not they have matching tuples and any tuples for lacking of matching values. So there's the difference between inner joins and outer joins is that inner joins rows from either table that are unmatched in the other table are not returned, while outer joins and matched rows in one or both tables can be returned. So outer join operations three parts. So first is left join. The left outer join operation keeps every tuple in the first or left relation relation R and R to S. If no matching tuples is found in S, then the attributes of S in the join results are filled or padded with null values. So as we can see in the merge table, rows are based on the left of how many rows are in the left table, and so kita na to since sa right table na tulo ka rows, then ang butang diri sa country kay null lang o wala ang po yung contra ID na number 4. So mostly gabase ang merge na version sa left join na table diri sa left outer join. So the next one, second is right outer join. The same lang siya sa left outer join, kaso sa right lang siya. So right outer join keeps every tuple in the second or right relation as in the result as third operation. So the same ulit sila regular pinagkuhan kay so makita to right table isa lang ka rows while left table ka upat. So sa merge table kay isa ra pud kay sa right isa. So the third one and last, full outer join keeps all tuples in both the left and right relations when no matching tuples are found, padding them with null values as needed. So in the full outer join kay merge jud tanan o same gyapon gina butang og null ang nga walay values or kanang kulang ang mga information. So chapter 8.4.5, the outer union operation. The outer union operation was developed to take the union tuple from two relation and also get the result relation. It is therefore the same as this operation will take the union tuples into relation R as x to x and y and s as x and z union compatible. The attributes that are union compatible are represented only that are partially compatible, meaning that only some of their attributes, say x, are relations that have some common attributes but are not union compatible. Once in a result in those attributes that are not union compatible from either full outer join and the common attributes. So mura to ko ang report. Thank you.
Good day everyone. My topic for today is talk about the example of queries in relational algebra. So the following are additional example to illustrate the use of the relational algebra operations. We will state each query in one way and leave it to the reader to come up with equivalent. So, this relational algebra is a widely procedural query language. So, nagakollect sad siya og mga instances, relationships sa input ug nagatag og occurrence sa relationships output ug ginagamitan sa niya ug mga various operation to perform these actions. So SQL relational algebra query operations are performed recursively on a relation. So ang output aning operation is bag-o na relation which mag-form siya og one or more input relations. And of course, we have the example. So query retrieve the name and address of all employees who work for the research department. So this is how you retrieve the name and address of employees. So of course, we must first put the research department, the department name research. So nga rin na to siya pagsundon kung unsa na to pag-retrieve ang names and address sa employees. And then this query could be specified in other ways. So dapat naka-specify siya sa lain nga pamaagi. So as a single inline expression is the query becomes. So mo na siya ang example sa to ang query number 1. Query number 2 is for every project located in Stafford, list the project number, the controlling department number, and the department manager last name, address, and birth date. So yan. So ato na i-list ang project number, ang controlling number, controlling department number, then the department managers, and the last name and address and birth date. So dapat naka kuan yun siya nga unahon dyan na to siya ang list kung asa siya ang located, diba? Just for the projects, the project number ito siyang i-list first. Then so kanin siya is we must first select the project located. So ito siya maotong ibutang ang located in Stafford, then i-join na to siya their controlling departments, and then join na po na to ang results sa department managers, then we finally apply the project operations on the desired attributes. So the query 3, find the names of employees who work on all projects controlled by department's number. So ato na po ibutang ang department number na sad. So mag-create ta og table, mag-create ta og department that contains project number sa term project nga naga-control siya by department. And then mag-create ta og table that holds tuples, then i-apply na to ang divisions operations. And then finally makabuhat na to maka-join na ta sa results sa division, which is magunit lang siya. For my next topic is talk about the tuple relational calculus. So in this section, we introduce another formal query language for the relational model called relational calculus. So our first topic, the relational algebra, and now we talk about the relational calculus. So in both variations of relational calculus, we write one declarative expression to specify a retrieval request, and there is no of how or in what order to equivalently a calculus expression specify what is to be retrieved rather than how to retrieve it. So the previous query retrieves all attribute values for each selected employee tuple. To retrieve only some of the attributes data, first and last names we write. So diri sa atong calculus is mag-start siya from our first name, last name, and the salary. Yan. And then this is the term. Formally, we need to specify the following information in tuple relation calculus expression. So for each tuple variable, the range relations, this value is specified by a conditions of for, and we do not specify our range relations. And then variable will range over all possible tuples and the universe as it not restricted in any one relation. So muna siya ang mga and tuple variable nga nastay range relations, and then nag-specified siya in the conditions of the form. So, a set of attributes to be retrieved, the requested attributes, the values of these attributes are retrieved for each selected combination of tuples. So, nagana siya at attributes na ma-retrieve ang imuhang buhat na query. So, the values na attributes in mag-retrieve din siya nga imong gina-select na combinations sa tuples. So, before we discuss the formal syntax of tuple relation calculus, considered another query. So, we have an example of query here to retrieve the birth date and address of employee. His name is John B. Smith. So, kung ato siya i-retrieve, atong ibutang ang iyang birth date, yung address, and then this the employee, and then the first name niya po niya. So maguna ang birth date, address, bago ang first name, and then ang iyang last name. Next is the expressions and formulas in tuple relational calculus. So a general expression of the tuple relational calculus is of the form. So an atom of the form where relational is a relation name, and tuple is tuple variable. So in this, it identifies the range of the tuple variable as a relation whose name relational. It evaluates the true if it is tuple in the relations, and evaluates the false other. We have the essential and universal quantifiers. In addition to special symbols, qualified quantifiers can be appeared in formulas. These are the universal quantifiers. So this is the truth sa atong values na formulas with the quantifiers nga naga-describe siya in Rule 3 and 4 below. And we have the sample queries and tuple relational calculus. So we will use of the same queries from sections 8.5 to give flavor or have the same queries specified in relational algebra and relational calculus. So ang atong first example is list the name and address of all employees who work research department. So atong ibutang ang first name, the last name, address, the employee, the department name, and the department number. Our next is the notations for query graphs, and we have this the example of the graph of our notations for query graphs. We have the project number, the department number, the last name, the address, the birth date, the department number, the manager, department manager, and the project locations, and yan, no, na to ang examples sa to ang query graph. So says transforming the universal essential quantifiers. So mala niyo siya ato ang lahi na quantifiers ato ang queries. And then using universal quantifier in queries, whenever we use universal quantifier, it is quite judicious to follow a few rules to ensure that our expression makes sense. We discuss these rules with respect to the query. So, amang na po na siya. So, same nagyapon siya. It depends lang kung unsa ang naguna sa iya. Ato ang list. So, is the names of employees, last name, first name, employee. So, can break up query 3 into its basic components as follows. So, dali lang kayo siya. Nato siya mabuhatan sa tongkwan. And then, muna na siya ito ang last. And save expressions. We never use universal quantifiers, essential quantifiers, conjugation, predicates, and calculus expression. We must make sure that the resulting expression makes sense. So, a saved expression in relational calculus is one of guaranteed to yield finite number of tuples as it resolved. Otherwise, the expression is called unsafe. For example, the expressions. That's all my report for today. Thank you and
The existential and universal quantifiers. Two special symbols called quantifiers can appear in formulas. These are the universal quantifier and the existential quantifier. So the universal quantifier is used uh, when some property holds for all elements of class, is denoted as foral in latex, while the existential quantifier is used when there exist some objects in a class that has some property and it is denoted as exist in latex. So we have we have to define the concept of free and bound tuple variables in formula. And informally, the tuple variables t is bound if it is quantified, meaning that it appears in an um, exist p or foral p clause. Otherwise, it is free. Informally, we define a tuple variable in a formula as free or bound according to the rules. So what are the rules? An occurrence of tuple variable in a formula F that is an atom is free in F, and occurrence of a tuple variable T is free or bound in a formula made up of logical connectives. And this is F1 and F2, F1 or F2, and not F1 and not F only F1 or not only F2. And depending on whether it is free or bound in F1 or F2. So a tuple variable may be free in F1 and bound in F2, vice versa. In this case, one occurrence of the tuple variable is bound and the other is free in F. And all occurrence of the tuple variable t in F are bound in a formula F. The form F is equals to exist t and F, or F is equals to foral t and F. The tuple variable is bound to the quantifier specified in F. So for example, consider the following formulas below. So to give more examples about that, example that I have a class of animals A and the following predicates C, x is equals to x is a cat, and m x is a camel. So then the statement all cats are animals are expressed as this one. And similarly, the statement that there exists a cat would be expressed as this one. So we combine the quantifiers together to say that things like for all something there exists something. So back to this, the tuple variable d is free in both f and f2, whereas is bound to the um, foral quantifier in f3, and variable t is bound to the exist quantifier in f2. So the exist quantifier is called an existential quantifier because of formula exist t and f is true. Exist are some there exist some tuples that makes f true, and the universal quantifier is true if every possible tuple that can be assigned to pre-occurrence of t in f is substitute for t, and f is true for every such substitution.
So good morning everyone. For today's topic, we will going to discuss the sample queries in tuple relational calculus and notation for query graphs. But before that, we will find out what's the meaning of a tuple relational calculus. It is stated above that a tuple relational calculus, it is a non-procedural query language that describes the desired information without giving a specific procedure for obtaining that information. Okay, some further definition about the topic. Relational model is based on the relational algebra, but we might equally will have said it is based on the relational calculus. While the algebra provides a collection of explicit operation, the calculus provides a notation for a formulation, the definition of that desired relation in terms of those given relation. For us to further understand what I am saying, so I'll give some examples of what is a tuple relation calculus and its formula.
As shown on this slide, a tuple relational calculus expression is of the form of a curly open bracket, T, and a vertical line, and the capital T, open close parenthesis, then T, then a close curly bracket. So, this expression is a query language. A query language is a high-level computer language for the retrieval and modification of data held in databases or files. Query languages usually consist of a collection of operators which can be applied to any valid instances of the data in structure types of a data model in any combination desired. In the context of graph data management, a graph query language or GQL defines the way to retrieve or extract data which have been modeled as a graph and whose structure is defined by a graph data model. Therefore, a GQL is designed to support specific graph operations such as graph pattern, matching, and the shortest path finding. So, let's go back to this expression. It is the set of all tuples T such that predicate P is true for T, where P is a formula. A formula may contain several tuple variables. A tuple variable is said to be unless it is quantified by a tree. There exists, or this kind of symbol means for all. Tuple variables that are quantified by tree or this symbol are called bound variables. Okay, for this example in this expression right here, where T and this kind of symbol, which means T lone, denotes that the tuple T is in a relationship to the lone. So, as we can see on this expression, T is a free variable, while S is a bound variable. What do you mean by that? A free variable has no limitation and isn't tied up in any way. It can represent whatever number it needs to represent. Also, the function or expression depends on the free variables. You can say that the value of free variables determines your answer. On the other hand, the bound variable is a variable with limitations, like it's in a jail. A bound variable cannot represent whatever number you need in 2. So it's possible the values have already been specified. Also, functions don't depend on their bound variables. So here's another set of sample queries. Finding the branch name, loan number, and amount for loans over $1,200. So here is the expression. So this query would mean, this query or this expression would mean the set of tuples T, where T and this sign means belongs to the loan relation and the loan amounts for each T is greater than $1,200. So now, let's discuss about the query graph notation. So what is a query graph? Query graph is sometimes also used for representation of a query. In a query graph representation, the relation in a query are represented as a relation nodes. These relation nodes are displayed in a single circle. These relation nodes are represented or displayed as a single circle. The constant value from the query selection are represented by constant nodes, displayed as a double circle. The selection and joint conditions are represented as a graph edge. Finally, the attributes retrieved from the relation are displayed in a square brackets. In the notation of the query graphs, the double ovals or the circles are used to represent constant nodes, while the single circle are also represented as relation nodes. The nodes which represent queries in the relations are classified as relation nodes.
Hello everyone, my name is Aldrine Perasol. I will be the reporter of Chapter 8 in Transforming the Universal and Existential Quantifier. We now introduce some well-known transformations from mathematical logic that relate the universal and existential quantifier. So, it is possible to transform a universal quantifier into an existential quantifier, and vice versa. So, to get an equivalent expression, one general transformation can be described informally as follows. Transform one type of quantifier into the other with negation, which is preceded by not, and or. Replace one another, a negated formula becomes a negated, and a negated formula becomes negated. Some special cases of this transformation can be stated as follows, where the triple bar stands for equivalent to. So notice that the following is true where the arrow symbol stands for implies.
Using the universal quantifier in queries. When we use universal quantifier, there are few rules that needs to be followed to ensure that our expression makes sense. Given the example above, we can now use the universal quantifier to list the names of employees who work on all the projects controlled by department number 5. The photos provided below will show you how query 3 was divided into its basic component. Nakakita ninyo gidivide siya sa tulo. F1, and F2. Nakikita ninyo. After divided into its basic component, we need to make sure that all the selected employee works on all the projects that was controlled by Department 5. And for us to do that, we will be using universal quantifier, which means that for this component to be true, we need to ensure that the inner formula must be true. For us to do that, we need to exclude the sequence that we are interested in. We want to make sure that the selected employee works on all the projects controlled by Department 5, but the definition of universal quantifier says that to make the quantified formula true, the inner formula must be true for all tuples in the universe. The trick is to exclude from the universal quantification all tuples that we are not interested in by making the condition true for all such tuples. This is necessary because a universally quantified tuple variable such as x in query must evaluate to true for every possible tuple assigned to it. To make the quantified formula true, the first tuples to exclude are those that are in the relation R of interest. In query 3, using the expression not project x inside the universally qualified formula evaluates to true all tuple x that are not in the project relation. Then we exclude the tuples we are not interested in from R itself in query 3. Using the expression not department number 5 evaluates through all tuples that are in the project relation but are not controlled by department 5. Finally, we specify a condition F2 that must hold on all the remaining tuples in R. Hence, we can explain query 3 as follows. For the formula F, we must have the formula F be true for all tuples in the universe that can be assigned to X. However, in query 3, we are only interested in F being true for all tuples of the project relation that are controlled by department number 5. Hence, the formula f is of the form not project x or f1. The not project x or condition is true for all tuples not in the project relation, has the effect of eliminating these tuples from consideration in truth value of f1. For every tuple in the project relation, f1 must be true if f is to be true. Using the line of reasoning, we do not want to consider tuples in the project relation are not controlled by department number 5, since we are only interested in project 5 tuples whose department number 5. Therefore, we can write muna siya f department number 5 then f2, which is equivalent to not department number 5 or f2. For number 3, formula f1 hence is of form not department number 5 or f2 in the context of query 3. This means that for a tuple x in the project relation, either in its department it's not equal to 5 or it's must satisfy f2. Finally, f2 gives the condition that we want to hold for a selected employee tuple, that the employee works on every project tuple that has not been excluded yet. Such employees tuples are selected by the query. Safe expressions. A safe expression is relational calculus is one that is guaranteed to yield a finite number of tuples as its result. Otherwise, the expression is called unsafe. Unsafe because it yields all tuples in the universe that are not employee tuples, which are infinitely numerous. Using the universal quantifier, we will get a safe expression. Also, we can define more precisely by introducing the concept of domain of a tuple relational calculus expression. In general, include tuples from outside the employee relation. Such value are in the domain of expression. The domain relational calculus. Domain relational calculus is procedural query language equivalent in power to tuple relational calculus. Domain relational calculus provides only the description of query, but it does not provide the methods to solve it. To form a relation of degree for a query result, we must have n of these domain variables, one for each contribute. An expression of domain calculus is of the form. Nakita ninyo. Where x1, x2, xn plus 1, xn plus 2, xn plus n plus m are domain variables that range over domains, and COND is a condition or formula of the domain relation calculus. A formula is made up of atoms. The atoms of a formula are slightly different from those for the tuple. That calculus can be one of the following. An atom of form are x1, x2, xj, where r is the name of a relation degree, j and h, x, j, j is a domain variable. This atom states that a list of values of greater x1, x2, must be a tuple in a relation whose name is r, where x is the value the I int attribute value of the tuple. To make a domain calculus expression more concise, we can drop the commons in a list variables. Thus, can write hence x1, x2, x and r cross parenthesis x1, x2, x3 close parenthesis, and instead of x1, x2, r open parenthesis x1, x2, x3 and gikuha wala agi tanggal diri ang kani quit and an atom of the number 2, an atom of the form x I OPXJ where OP is one of the comparison operations in the set and XI and XJ are domain variables. Number 3, an atom of the form XIOPC or COPXJ where OP is one of the comparison operation in the set. Xi and Xj are domain variables and Cs is constant value. In tuple calculus, atoms evaluate true or false for a specific set of values called the truth values of the atoms. In case 1, we can say that if the main variables are assigned values corresponding to tuple of specified relation R, then the atom is true. In the case 2 and 3, we can say that if the domain variables are assigned values that satisfy the condition, then the atom is true. Example, as we mentioned earlier, it can be shown that any query that can be expressed in the basic relational algebra can also be expressed in the domain of or tuple relation calculus. Also, any safe expression in the domain or tuple relation calculus can be expressed in the basic relation algebra. The QBE language was based on the domain relation calculus. Also, this was realized later after the domain calculus was formalized. QBE was one of the first graphical query language with minimum syntax developed for database systems. It was developed at IBM Research and is available as an IBM commercial products as part of the Query Management Facility or QMF interface option to DB2. The basic ideas used in QBE have been applied in several other commercial products because of its important place in the history of relational language. We have included an overview of QBE in Appendix C.